Let's start with the core idea of the chapter. How fast a reaction happens, what the rate law tells us, and which factors change that rate. Chemical kinetics is about speed, not just possibility. That is why this chapter sits beside the stopwatch, the transition state, and the energy profile. It is the study of reaction pace, not reaction destiny. Before anything else, separate three ideas that students often blur together. Thermodynamics asks whether a reaction is feasible using delta G less than 0. Equilibrium asks how far the reaction will go. Kinetics asks how fast it will happen. A reaction can be thermodynamically feasible and still be practically useless if it is kinetically too slow. That is the real trap here. Feasible is not the same as fast. Reactions can be grouped by speed. Ionic reactions are usually instantaneous. Molecular reactions are typically moderate in speed. Oxidation reactions can be extremely slow, like rusting of iron in air and moisture. Kinetics is mainly interested in the middle ground, where speed can actually be measured, studied, and manipulated over time. The rate of a reaction is the change in concentration divided by time taken. For reactants, rate is written as minus delta R divided by delta T. For products, it is plus delta P divided by delta T. The negative sign for reactants does not mean negative speed. It only reflects that reactant concentration falls as the reaction proceeds. The overall rate is always treated as positive. The same rate idea looks different in different systems. In an aqueous lab, concentration is expressed as molarity. So the unit of rate becomes moles per liter per second. In a gas chamber, concentration is tied to partial pressure. So the unit becomes atmospheres per second. Here is a trap you need to be aware of. Do not use molarity units for a pure pressure-based gas question. The state of matter tells you the correct dimensional form. There are two common ways to describe rate. Average rate is the overall change over a macroscopic interval, so it gives the trip's overall pace. Instantaneous rate is the rate at a specific moment, found as the limit where delta T approaches 0. Mathematically, it is written as R instant equals minus dr by dt equals plus dp by dt. This distinction matters because averages smooth out details, while instantaneous rate captures the exact point behavior.
The graphical method makes the idea concrete. On a concentration time graph, the slope of the tangent at any point gives the instantaneous rate. The secant line gives the average rate. In the example shown, the tangent at around 600 seconds gives the instantaneous rate value. This is one of those places where the graph is not decoration. The graph is the answer.
When a reaction has several species, the stoichiometric coefficients must be handled carefully. In the example with two HI forming H2 and I2, HI disappears twice as fast as H2 appears. To compare them on one common scale, divide each species rate by its stoichiometric coefficient. That is why the universal rate is written as rate equals minus 1/2 multiplied by delta HI divided by delta T equals plus delta H2 divided by delta T equals plus delta I2 divided by delta T. Here is a trap you need to be aware of. Do not compare raw concentration changes without correcting for coefficients.
The same logic extends to any full reaction expression. For 5 bromide ions plus bromide ion plus 6 hydrogen ions forming 3 bromine molecules and 3 water molecules, each species contributes to the rate with a coefficient-based factor. Reactants carry negative signs because they disappear. Products carry positive signs because they form. The formula written here is the full stoichiometric rate expression. and it is exactly how you unify all species into one reaction rate.
The rate of a reaction changes because the system changes. Four major factors are highlighted here. Concentration increases collisions when particles are crowded together. Temperature raises kinetic energy and accelerates reaction speed. Catalyst lowers the activation energy barrier without being consumed. Surface area increases the number of exposed reaction sites. These are the four levers behind most kinetics questions. Let's summarize the topic. Average rate uses change over time, delta, giving a macroscopic view. Instantaneous rate uses d over dt, the slope at a single point, a microscopic limit. Curve down means reactants are disappearing. Curve up means products are forming. The slope of the tangent line equals the instantaneous rate. For units, aqueous solutions use moles per liter per second. Gases use atmospheres per second. For AA to BB, rate equals -1 over A times dA over dt and positive 1 over B times dB over dt. We hope that you have understood the topic. For more such content, explore EduRev app.